Okay, welcome back. So now we're going to finish our discussion of molecular orbital theory and expand into when p orbitals come into the picture. So when we start getting into molecules where we involve atoms that have p orbitals, we need to think about how molecular orbitals are going to be formed from the p orbitals. So at the beginning here, of course, again, we're looking at a simple sort of pairwise. But, of course, when p orbitals, there are 3 of them. So there's 3 pairs. Now, one of those pairs will combine in a straight-on sigma-type end-to-end overlap, and therefore will generate sigma molecular orbitals. Now, we sort of just arbitrarily designate that as the px. Now, this is similar to what we saw with the s orbitals, right? We form a stabilized bonding order that has a bonding orbital, which we call the sigma 2p, that has a lot of density here along the bonding axis. We form a destabilizing or higher energy antibonding sigma star 2p that shows the electron density is outside the bonding, right? Now, what about the other 2p orbitals? Now, of course, if all of these are, in orientation, they can't all overlap end to end, right? Because these other orbitals are located 90 degrees, from the px, right? Either along the y-axis or the z-axis. So these two are forced to combine in a side-to-side way, or a pi combination. And so we generate, instead of generating sigma molecular orbitals, we generate what are called pi molecular orbitals. And each of these combinations will generate a pi 2p and a pi star 2p with generally the same kinds of characteristics, right? The bonding is lower in energy and emphasizes overlap, right? It shows overlap between the lobes. Whereas the anti-bonding orbitals show a lack of electron density where the overlap should be, right? And of course, the other one is so the PZ in this case, is going to make similar types of orbitals, but along a perpendicular axis, or 90 degrees apart. So we have the pi 2p, and again, this one will look similar, it's just you can't see what this kind of space is, right? But there's clearly a node here. But the idea is that we're seeing where there would be overlap here and here. You can see these are sort of spaced apart. We see a lack of bonding, and so we get another pi 2p and a second pi star 2p. So overall, we generate a pair of pi 2p orbitals and a pair of pi star 2p orbitals. So we combine our 6 p orbitals, right? 3 from each of the atoms, and we get 6 new molecular orbitals. Now, let's put these on our diagram. So notice here we're showing just the valence electrons, right? So the 1s orbitals are no longer shown, but we're showing the sigma orbitals that come from the 2s, and we're showing the pi orbitals that come from, the pi and the sigma orbitals that come from the 2p orbitals. So notice we have 2 orbitals down here. We have a total of 6 orbitals. Also notice we've grouped the pi orbitals, the bonding pi orbitals, and the anti-bonding pi star orbitals, so there's sets of 2. Now again, we focus on this center part, right, when we do this, because these are becoming these, right? We're combining these. So the only orbitals that are important to us are this center column, the molecular orbitals. Now, anytime we do this kind of stuff, we start putting electrons in, we're going to follow just what we've always done when we've occupied orbitals with electrons, right? We start with the lowest energy and we build up, right? And so that's exactly what we're going to do here. And we can see the energy order where our sigma orbitals that come from the s orbitals are lower in energy because the original s orbitals, right? If we think about the atomic orbitals, right, there's an energy order. And so if the atomic orbitals are lower in energy, then the molecular orbitals they generate while they go higher and lower based on that starting point, on the overall energy scale, those orbitals are going to be lower. Now, the order of these orbitals is determined computationally. Now, I'm going to point out one sort of significant change that occurs. So, notice these orbitals here, the sigma 2p and the pi 2p, right? They change order. So, this is for the early p orbitals, right? Or the early p block elements. So, in this case, boron, carbon, and nitrogen for the 2p's, for the second period, and oxygen, fluorine, and neon, the later ones. So, what's going on here? Now, while we're not going to dive deep into what's going on here, we can talk about it a little bit here. So, let's take these overall pictures, and we're going to look here. Now, I'll point this picture out here. Notice we've eliminated the atomic orbitals for simplicity. So all we're looking at is that middle section of the diagram, the molecular orbitals. But if we focus on this picture in the corner here, notice that one of the things that we simplified here is that we mixed pairwise. Right, so we just combined the 2s on one atom with the 2s on the other. Right, it just left it at that. But notice it's a little bit more complicated picture because in actuality the 2s and the 2px combine in a very similar way. So if you notice when those s orbitals go together, they go in a sigma fashion. When the p orbitals come together, they come together, the px orbitals, they come together in a sigma fashion, right? They both generate sigma orbitals, whether they're sigma 2p or sigma 2s. So in reality, the mixing, we can get combinations of mixing where the 2s's and the 2p all mix together to give 4 orbitals. Now, this mixing occurs to sort of different degrees, right? And we can sort of see that here, right? So if we have this kind of picture that we see in oxygen, fluorine, and other, where the sigma 2p is lower than the pi 2p, that comes from, not very much mixing, right? So we're sticking to sort of the pairwise mixing. Whereas in the early elements, we're seeing more mixing, and the result is the sigma 2p gets higher in energy than the pi 2p. So we see a flip-flop here of these energies based on the amount of mixing, when we say mixing, remember we're talking about mathematically mixing, right? When we combine the wave functions, right? So are we combining just the 2s with the 2s? Or are we combining all of those wave functions together, right? To some extent. And so it's that level of what we call S and P mixing that affects the order of these orbitals. Now, why do we see a little bit more mixing, here? Why do we see more mixing here than we do here? Well, it really comes from the energy of the atomic orbitals. So in B2, C2, and N2, the original atomic orbitals are closer in energy, so when they mix, it's easier for them to all mix together, right? If there's a lot of energy difference between the S and the P orbitals, then they're not really going to overlap when they mix. We're going to see that nice pairwise. But if the 2S and the 2P are close in energy originally, then we can sort of see them, kind of mixing crosswise, and we get this more complicated S and P mixing that goes together. So, and it turns out that in boron, carbon, and nitrogen, those atomic orbitals are closer, so we see more mixing. As we get over to oxygen, fluorine, and neon, the energy spacing is greater, so we see less mixing, and so we see this order instead of this order. Now, fundamentally speaking, it really doesn't affect the outcome of some of the simple stuff that we're doing. So, for example, if I used either set of ordering to calculate the bond order for one of these elements, I would come up with exactly the same. And so if I went to calculate, different properties, I would still come up with the same. If I went to calculate paramagnetic or diamagnetic, no matter what order I used, I'm going to come up with the same answer. So it doesn't really affect the outcomes, but it's more about what's really taking place. Right? Okay. Now, again, just as more of a background, I'm not going to, dive deep into asking you questions about S&P mixing. But what we want to focus on is how to fill one of these. Now, I am more likely to ask you to fill one than to actually draw them out. So I will probably provide the correct order, right? I may ask you a question about the ordering, but if I actually ask you to use a diagram, I will provide that diagram for you, not actually have you draw the diagram with the correct ordering. Okay, but let's survey those period 2 diatomics. And let's just go across. So we see that, for boron, right, we get a bond order of 1. Okay, so B2 is nice and stable. For C2, we get a bond order of 2. Okay, notice the bond is stronger bond, shorter bond, right? Remember, higher bond orders indicated with stronger, more bond energy, shorter length. N2, notice a triple bond, bond order 3. Now, I'm going to point out here that remember this triple bond? That matches our prediction from Lewis theory, right? So we can see that Lewis theory was giving us a lot of good information, right? It predicts a triple bond. Triple bond is what we see when we look at it from an NO perspective as well. O2, again, double bond, just what we saw in Lewis theory. And we can see the higher the bond order, again, higher energy, shorter bonds. F2, again, stable, but a single bond. So now, we get to the noble gases, as we saw with helium. Notice, they're all filled. Bond order of 0 doesn't exist, right? Neon exists as individual atoms. And so we can calculate all of these bond orders. And what I would ask you to do, or what I would challenge you to do to get a little more practice, is to use our bond order equation and make sure you can come up with these answers, right? So number of electrons in bonding orbitals minus number of electrons in antibonding orbitals divided by 2. So we can do one example for oxygen, let's say. So if I look at oxygen, if I look at all the bonding orbitals, right? So we got a bonding here, we have bonding here, we have bonding here. And so in those bonding orbitals, we have 2, 4, 6, 8 electrons. If I look at the antibonding orbitals, I have my pi star here, I have my sigma star, I have my sigma, and then I have my pi 2p star with electrons. And they have a total of 2, 4 electrons. 4 electrons in antibonding. So that's how we come up with this. Now, we're going to go on to talk about this a little bit, but notice also right here, O2, right, contains unpaired electrons, according to MO theory here. That would indicate that O2 is paramagnetic, right, not diamagnetic as predicted previously. And right, we've pointed out that this is one of the weaknesses that we see with our earlier theories. So O2 is paramagnetic. I'll also point out that B2 would be paramagnetic, right, with the unpointed electrons. All of these diatomics would be diamagnetic because everything is paired up. So now we have a theory that correctly gives us the magnetic properties of dioxygen, or O2, right? It is going to be paramagnetic, right, because it has those unpaired electrons. Even though in Lewis theory and in valence bond theory, right, everything looks like it's paired up. Now, experimentally, we knew this was the case, right? This is liquid oxygen in between two magnets. And we can see, look at that liquid oxygen. It's floating, right? And that's because all of the little unpaired electrons there are matching up in terms of the direction. And they're spinning, right? And so those spinning charged particles generate a magnetic field that interacts with the external magnetic field from those magnets, and they attract each other, so they stick. It's really kind of cool looking, right? That doesn't fall here, sticks between the magnets. Now, so far we've done simple homonuclear diatomics. You can also do heteronuclear diatomics. Now, we're not going to go into as much detail on these clearly, but the idea is that if you combine atomic orbitals that are identical in equal energy, meaning the same atom, it's really easy just to combine them to form the molecular orbitals. But if those starting atomic orbitals are of different energies, like, the 2s orbital of nitrogen is not going to be the same as the 2s orbital of oxygen in terms of its energy, right? The overlap in the mixing becomes a little bit more complex. And we get unequal mixing, if you will, in terms of generating the molecular orbital. The more electronegative atom is the one that will typically have lower energy orbitals and therefore is going to contribute more to the molecular orbital, to the bonding molecular orbitals. The higher energy atomic orbitals will become more part of the anti-bonding orbitals. And so we just get a more complicated mixing picture. So if we kind of look at this, we can look at NO, for example. And the thing is to look at, if you look at the atomic orbital part of this diagram here and here, notice the original orbitals are not of the same energy. So the N2s is a little bit higher energy than the O2s. So when they form, the bonding orbital, right, is more like the oxygen, right? The antibonding orbital is more like the nitrogen, if you will, right? So it contributes more to the one that it's closer in energy to. So the higher energy atomic orbital contributes more to the antibonding. The lower energy atomic orbitals contribute more to the bonding. And we see the same thing with the P's, right? So the bonding 2p molecular orbitals, the sigma and the pi's, will have more of the oxygen characteristic, if you will, and the antibondings will be more like the nitrogen ones. And so maybe some of the result that we see here is that notice the electron density is more around the oxygen, right? And oxygen being lower in energy, higher electronegativity, right? So we have lower energy atomic orbitals, is going to contribute more to the bonding orbitals, where we have the electron density. So that lower electronegativity, lower energy atomic orbitals contributes more to the bonding orbitals, and so those electron densities in those bonding orbitals are going to be closer to that higher contributing atom, is what it comes down to. Now, again, getting a little to the details here, but just trying to give a little bit more background. You can calculate the bond order here. So we have 2, 4, 6, 8 electrons in bonding. We have 2, 3 electrons in antibonding. So we get a bond order of about 2.5. So you might predict a double bond here in terms of Lewis theory. But we have an actual bond order, or predicted MO bond order for about 2.5. And we'd predict it's paramagnetic because of the unpaired electron. Now, we talk a little bit about delocalization and this helping us with delocalization. So let's look at ozone, right? Remember ozone, we had 2 resonance structures. Valence bond theory, right, shows a double and a single bond, right? So we can't express the hybrid structure, but remember in the hybrid, we would visualize that each of these bonds is kind of like a bond and a half, right? So when we do our molecular orbital theory and we can generate orbitals that encompass the entire molecule, not separated, located on individual atoms, we can now form a single orbital that explains, or we can form a bonding orbital that explains or shows this kind of delocalization. Now, again, this is going to become more complex because now we have more than 2 atoms. And so when you have many atoms that are combined, the atomic orbitals of all those atoms are combined to make a set of molecular orbitals, which are spread out or delocalized over the entire molecule. And of course, this gives results that more match up with what we know is the truth, right? So this molecular orbital is much closer to what we would imagine as the hybrid, right? Where the electrons are spread out over the entire, not isolated on one side or the other. So we can help explain delocalization. Now, of course, we can go on to bigger and bigger molecules here. So I'll just show you one last picture, and that is what we call benzene, right? So C6H6, and we can see within this ring structure, there are 3 double bonds and 3 single bonds. Now, in reality, this is what we can show via Lewis or valence bond. But of course, I think it's, makes more sense based on what we've already learned that all of these bonds are identical, right? There's no experimental evidence that shows that those bonds are any different from one another, right? So we don't really have 3 double bonds and 3 single bonds. We have 6 bonds that are all the same. And if we look at a particular bonding orbital of this, that gives us a better picture where, again, the electrons are dispersed throughout the entirety of the 6-membered ring, right? They're not more on one side or the other. They're delocalized over all 6 carbons. And again, this delocalization is good. It makes these molecules stable, right? All right. So we're going to stop here, wrap it up. Hopefully now we have a better understanding of bonding theory in general and just molecules and bonding. But by looking a little bit at molecular orbital theory. And just to go back, when I ask you questions about MO theory, sort of the big ideas that I want you to understand are some of how is it done, so the basic idea of linear combinations of atomic orbitals, right? What are we actually sort of doing, right? That we're taking the atomic orbitals and mixing them, again, mathematically, estimating, right, to create new orbitals, right? So, and those new orbitals are no longer atom-based, they're molecule-based. So we have molecular orbitals, not atomic orbitals anymore. And these molecular orbitals can give us a better picture of the bonding over the whole of the molecule. And I want you to be able to apply this in such a way that you could fill up an MO diagram, you could calculate bond orders, you could predict paramagnetic and diamagnetic, and so forth. And you would know that molecular orbital finally gets us to a place where we can have a better explanation or a better theoretical picture of things like electron delocalization and resonance, and show, why those things are true. So we can get, again, reality, experimental, what we see matches the theory, or vice versa if you want to think about it that way. Okay, so we'll wrap that up. Next time I talk to you, it will be about chapter 12.